Good morning, good afternoon, good evening, wherever you might be, and welcome to another science post. This one is on imagining an atom. You can picture an atom as empty space filled with an invisible cloud of probability, which, when disturbed, instantaneously becomes a point-like electron. Or you can imagine an atom as a moving, stormy, kinetic thing which really exists in the same way that a galaxy of stars or the winds of a hurricane exist. The picture in the blog post linked below is of an atom, a hydrogen atom, and it was constructed by using light pulses to kick hydrogen's electron out of the atom and onto a detector. After doing this over and over, they reconstructed a picture of hydrogen. Of course, as in the case of the reconstruction of an image of a black hole, there are open questions about how picking and choosing your data will influence the image you produce. There are also reconstructions from different diffracted X-rays, reconstructions of atoms from diffracted X-rays, but they're not really pictures in a conventional sense. And I have some pictures in the blog post below. The reconstructed images of atoms can be compared to mathematical models of an atom showing regions in which an electron is likely to be found. Two popular models are the Bohr model and Schrödinger's model. In each picture, there is a standing wave between the electron and the nucleus. And in Bohr's model, or in the pilot wave interpretation of Schrödinger's model, the wake of the electron is literally hitting the nucleus and reflected back to the electron. The two models agree in most of their predictions, but each runs into complications, and each makes different approximations when dealing with the details of spin. I can tell you that the angular momentum, which is mass times velocity times the radius, of the orbitals is quantized in amounts defined by an integer times Planck's constant over 2 pi. And that Planck's constant times a unit of mass over time is the surface area of a bubble. But somehow I cannot tell you exactly what an atom looks like. Using a definition of mass from fluid dynamics, you can picture an electron propagating around a nucleus like a boat with a wake, as shown in the picture in the blog post. As a sort of Ouroboros wiggling its tail. The electron moving around the nucleus will form a closed loop with the wake, and when the electron speeds up by a small amount, it will be pushed back into a valley of the wake. If the electron gets a big kick, which causes it to jump into another valley, this will produce a quantized absorption or emission of energy from the system. In a sense, the electron rides on its own wake, like a surfer. This is very similar to the description of processes in a free electron laser or in a synchrotron. Yet students everywhere are instructed to ignore the Bohr planetary model of an atom because the physics of synchrotrons tells us that such a model predicts that the electrons would radiate away all of their energy as synchrotron light and then crash into the nucleus. But is this true? The standard answer to this question is to roll your eyes and say, You have to solve the nonlinear Schrödinger equation, of course, or just grunt electron degeneracy pressure or Pauli exclusion principle, as though that is a good, satisfying answer. You probably know that an electron beam, which is accelerated or bent or turned by a magnetic field, will emit synchrotron radiation if it is relativistic and cyclotron radiation if it is not relativistic. So why wouldn't an electron, which is traveling around a nucleus, do the same thing? To answer this question, we must first know how fast electrons are traveling around a nucleus. And this turns out to be around 1/137th of the speed of light, or 1 over the fine structure constant times the speed of light. Or wait, no, that's not right. It's the fine structure constant times the speed of light. This is why non-relativistic estimates work so well for describing hydrogen. Using the cyclotron as a model for an atom, the formula for average energy radiated per unit time is given in terms of the Thomson cross-section multiplied by the magnetic field squared and the velocity squared, and then all of this is divided by the speed of light times the vacuum permeability. So to calculate what this might be for hydrogen, we could make an estimate for the magnetic field of the nucleus. Say the magnetic moment for our nuclear spin is 3 × 10⁻⁸ electron volts per Tesla. And for our electron, it is 2 × 10⁸ electron volts per Tesla. An electron or nucleus placed in a magnetic field will wobble or precess around at the Larmor frequency. We have an electron wobbling in the magnetic field of a proton, and a proton wobbling in the magnetic field of an electron. But what sort of a dance might they execute? The electron will orbit the proton, but the proton will also be orbiting around a central point, wobbling. The energy of the electron in the ground state, or the lowest possible orbit, is 13.6 electron volts. So I will use that to estimate a magnetic field of 13.6 divided by 2 times 10⁻⁸, and that gives 3.5 × 10⁻⁸ Tesla. This is the field necessary to keep the orbit stable. Plugging this all into the cyclotron equation, we get that the energy change per second due to cyclotron radiation is 1 Tesla amp meter squared, or volt amp second, or joule. 1 joule? That can't be right. Even if I messed up the calculation, the only acceptable number is 0. Otherwise, atoms can't exist, unless the same amount of energy is being radiated by the proton at the same time that the electron is radiating. If they are constantly trading energy back and forth in the form of photons, that would make a stable atom. 1 joule, huh? Wouldn't that be something? One can imagine that the electron and proton are each holding the ends of a rope, which they are wiggling up and down to emit photons. The proton and electron wiggles are completely out of sync, such that the rope at any given moment is perfectly flat, even though they are each shaking it up and down vigorously. It has 0 kinetic energy between them. destructive interference. If that stretchy rope has to get shorter or longer when the electron moves from one orbital to another, so both closer or further away from the nucleus, it must release or absorb energy, light, in an amount given by Planck's constant times the frequency with which the rope had been shaken. Such a transition produces, for example, the hydrogen spectral series, or, for hyperfine structure, the hydrogen line. The further out the rope is stretched, the higher the frequency and the higher the energy the emitted photons will have when the electron transitions to a lower orbital. By stretching the rope, the emitted or absorbed light wavelength gets shorter because the tension is greater. Just think of a guitar string. And that is why electrons will emit radiation when they make a transition from a higher orbital to a lower orbital, but they don't emit radiation when they are in a stable orbit. And I think the same is true for planets and moons in terms of, I guess you might call it, instead of light, you might call it a graviton, but you can also think of light as made up of gravitons or gravitational waves or whatever it is. Another nice model of an atom can be found in Chladni plates. And I have a nice video of what a Chladni plate looks like. And the mathematical model of this was developed much back in, was it the 1600s or the 1700s, by Sophie Germain. And it is markedly similar to the mathematical model that made Erwin Schrödinger famous. Yep, hundreds of years later. The Chladni plate was also studied by Leonardo da Vinci. But if you prefer more ancient models of the atom, you could try that of Cleopatra the alchemist. She also seemed to understand something about recursion. Way back in 300 BC, it was 400 AD, or something like that. Around the time when the Library of Alexandria burnt to the ground and Hypatia of Alexandria was burnt by nutcases. So now that we have some mental images of atoms, maybe we can make some pictures of electrons to go along with them. We know that electrons have charge and that they spin and act like magnetic dipoles. But how is an electron always spinning without losing energy? One answer is that the ether, zero-point energy, electron degeneracy pressure, vacuum energy, virtual particles, or whatever you call the fluctuating energy density of space, is constantly driving a pressure gradient around the electron. When a pressure gradient encounters a point-like disruption, like a stone in a stream, the pressurized space will swirl around the stone, and when the pressure gradient tends to come from one direction, you get clockwise swirls, which make an electron, or a spin up, or a negatively charged particle. And when the pressure gradient comes from the other direction, you get a counterclockwise swirl, which makes a positron, which is the same thing as a spin-down particle. As in Feynman's explanation of how magnetic fields are created by moving charges due to length contraction, electrons act like, or are, each other's antiparticles when they are moving in opposite directions relative to each other, as they are known to do when they share a shell while orbiting a nucleus. In order to understand why the behavior of spin is quantized, it is helpful to first understand the concept of a drag crisis in fluid dynamics, where when the velocity to viscosity ratio increases above a certain threshold, the drag coefficient sharply drops, and this allows a vortex to persist. While I have been through all of the quantum field theory jargon, I prefer a fluid dynamics way of thinking to the spin isn't really spinning, it's an abstract concept with no physical analog ways of modern physics instruction and quantum field theory. One can entirely avoid quantum field theory by using the model from condensed matter physics, in which the electron splits into the spinon, orbiton, and holon via spin-charge separation. This picture caused me to start thinking of the electron as a solid, spinning object, a spinon, surrounded by a swirling fluid, a holon, and separated from the nucleus by some space, an orbiton. And this is very similar to a planetary model. Something pulls us down to Earth because there is an exchange of gravitational waves between collections of atoms. When averaged out, the standing wave looks like your standard general relativity curved space-time picture. The waves are exchanged because space itself is oscillating. Something in the Earth pushes up on us because there is an exchange of electromagnetic waves between an electron and the nucleus. The waves are exchanged because space itself is oscillating. It seems to me that particles have angular momentum and charge because there is a rigid, spinning bubble-like thing and a current of fluid that swirls around it. The rotation of the rigid thing corresponds to our standard notion of angular momentum. The swirling current of fluid corresponds to our notion of charge and flowing charge, creating a magnetic field. Opposite charges are swirling in opposite or like directions, and the currents associated with those swirls attract or repel one another. When the swirl is fixed in one location, the swirl only has a magnetic moment. But when the location of the swirl begins to move, it acquires an electric dipole moment. You might have noticed that I was careful not to use the word spin in the above text. The word spin has been co-opted in an unfortunate way so that it is more closely associated with charge than it is with angular momentum or vorticity. This is the reason why the difference between positrons and electrons is the same thing as the difference between spin-up and spin-down particles. If this is hard to understand, it helps to remember that angular momentum is a property of the flow of mass, while magnetic moment is determined by the flow of charge around the particle center. They interact, but they are not the same. They have a constant of proportionality called the gyromagnetic ratio, which is not really constant because of, if you know about Larmor precession, as when a particle's spin precesses due to its magnetic moment and gravitational moment, in the same way that the axis of a spinning planet precesses due to its magnetic moment and gravitational moment. We know that spin flip is quantized, as in it happens instantaneously. But why is it quantized? It isn't mysterious, and it becomes clear if you have a proper interpretation of the Stern-Gerlach experiment, which is frequently taught to emphasize the weirdness of quantum mechanics when it's nothing. It's not weird at all. The experiment showed that since the charged particles were only ever deflected down or up, and nothing in between, the charged particle's spin is always quantized. In the rest frame of a particle bunch, the individual charged particles are traveling either forwards or backwards due to their shot noise. And since an electron traveling backwards looks like a positron to the electron traveling forwards, the reason that the particles are deflected either up or down and nothing in between is because they are either electrons or positrons, and it is not possible for some intermediate sort of particle to exist. The reason that electrons or positrons or spin cannot exist in an intermediate state is because they cannot be going in two directions at the same time. It's that simple. If a particle is moving away from you, it is a positron. If it is moving towards you, it is an electron. And there is nothing unique about these two particles other than the direction of their travel relative to you. I hope this simplifies the language of physics for you, because there's a lot of misdirection and over-definition of these things. Wait, you might say. If the bunch of particles is made up of electrons and positrons in the rest frame of the bunch, then why don't they annihilate? The reason is that a high-energy beam of particles is largely frozen in its rest frame, so there will be no collisions at high energy, while a low-energy beam of particles tends to transversely diverge too quickly for the forwards and backwards moving particles to interact in a destructive fashion. It is only in the high-energy environment of a collider or in a short circuit that electrons and positrons annihilate. So a good example of an antimatter bomb or a collision of electrons and positrons is nothing more than an arc welder, something they've been doing since ancient times. So for example, if you look at a Feynman diagram of the annihilation of an electron and a positron creating a photon which decays into a new electron-positron pair, what you're really looking at is the moment when an electron and a positron pass in front of you and turn into a positron and an electron. If I want to extend this picture to describe how an electron undergoes a state change to become a muon, or how a muon melts off a layer to become an electron, I have to define 4 sorts of substance. One is solid, one is space, one is energy, and one is fluid. And they all obey a very simple rule. Energy appears to push space, which will turn into fluid when it encounters a solid. And if I translate this into more archaic language, we get fire appears to push wind, which will turn into water when it encounters earth. Something you might find in ancient texts about physics, which is just, I find it hilarious that we've come so far and yet there we are. We're still in the same place we were. So I bet people like Cleopatra the Alchemist and Hypatia of Alexandria understood all of these concepts very well. However, I doubt that they knew why spin 1/2 fermions must go through 720 degrees to equal the 360 degrees rotation required by spin 1 bosons. When I was in school, I found it very confusing to be told that A photon in free space is a massless boson with spin 1, which rotates through 360 degrees and acts like a classical particle with respect to its angular momentum, while a photon trapped in a two-dimensional film is a massive fermion with spin 1/2, which rotates through 720 degrees and has half of the angular momentum you would expect from a classical particle. First of all, what is angular momentum for a massless particle? It means that there is rotation, but the rotation is not localized enough to qualify as massive. When the rotation gets trapped in a surface, it becomes massive. So, second of all, what do the terms fermion and boson add to my understanding? In truth, they add nothing to your understanding. They just make the language sound sillier and pay homage to some of the silly men from the past. Third of all, what is spin? Well, when you multiply the spin by Planck's constant, you get something called the intrinsic angular momentum of a particle, a concept that is only loosely related to the angular momentum, and more closely, oh hi doggy, more closely related to the charge, a quantity describing the circulation of electric current around a particle. A photon in free space has intrinsic angular momentum equal to Planck's constant, the smallest possible change in angular momentum in free space. A photon trapped in a film has intrinsic angular momentum equal to half of Planck's constant. But where did half of the angular momentum go when the photon got trapped in the film? The answer is that conservation of angular momentum requires that the photon in the film goes through 720 degrees of rotation, while a photon in free space only has to go through 360 degrees of rotation. In this case, angular momentum is conserved, but intrinsic angular momentum, or spin, is not conserved. I think the concept of spin has just messed people up. We need to get back to those classical concepts like vorticity. In what sense does the spin 1/2 photon behave non-classically? It's the last question here. It only behaves non-classically if you assume that it didn't change in shape when it transformed from a spin 1/2 particle into a spin 1 particle into a spin 1/2 particle. And that is clearly not the case. So I don't really know why anyone ever says the spin of particles doesn't behave classically, or the angular momentum doesn't behave classically, because the angular momentum behaves classically, but the intrinsic angular momentum, or spin, is just a weird concept. So I think that they mean that they run into they create a straw man in quantum mechanics instruction when they say that the electron is like a solid ball of charge, because it's clearly not. Spinning particles act perfectly classically if you treat these spin 1/2 particles as spinning surfaces, like an electron would be a spinning surface, a bubble, and a spin 1 particle is treated as a spinning volume. So there is no need to tell students that spin is a mysterious, non-classical, abstract thing, as I was actually told in some of my classes. That just confuses them. It actually alienates the sort of students who really want to understand things, and it only selects the sorts of students who are comfortable with just giving up and trying to do the math and not trying to understand anything. So what we have here is that a rotating volume usually has half of the moment of inertia of a rotating surface, and this is why an intrinsic angular momentum equal to half of Planck's constant, it's a spin one half fermion, corresponds to a movement which couples to a surface, and an intrinsic angular momentum equal to Planck's constant, or that's in a spin 1 boson, corresponds to a movement which couples to a volume. You can motivate this with comparisons of the inertia of solid cylinders and hoops, and the more mathematically inclined people can entertain themselves by calculating the results for more complicated shapes. So no one has been able to directly measure the radius of an electron, but that is no surprise since bubbles are rather ethereal things, and you have the classical electron radius, and that's the radius of a bubble, more or less. Once you stop disturbing the turbulent flow which has given rise to the electron's cavitation, it will reappear. So what I'm trying to get at in this video is a return to basic physical intuition that applies at all length scales and that does not confuse approximations with reality. By using words instead of equations, one maintains sufficient uncertainty to capture reality more accurately. And when one aims for too much mathematical precision, one invariably misses the mark when you're trying to imagine an atom. When I imagine an atom, I imagine each unit of empty space containing a unit of time divided by a unit of mass, a quantity that describes a unit of vibration and rotation. Because every unit of space already has some vibration and rotation in it, when something exists, it must interact with the vibrating and rotating space that surrounds it. This forces the object to move around and obey an uncertainty principle in which Planck's constant is the minimum momentum or position change allowed in nature. It is the area of a unit of space given by a sphere with a radius defined by the amount of vibration and rotation of the center. When two of these spheres are vibrating in sync, they will be attracted to one another as in an atom. When they are out of sync, they repel, as in two electrons traveling in opposite directions in an orbital. When lots of these spheres are packed together and moving in sync within a potential energy well, described by Laplace or by general relativity, there is a gravitational field. And when you try to calculate the local electric field from a synchronous oscillation responsible for gravity, you have to solve the problem of renormalization. And this is something that material scientists are rather good at because they tend to stick to a Cartesian coordinate system and renormalize things without the nonsensical stretching and contracting of spaces that is so common amongst those who are indoctrinated with Lorentz and Maxwell's equations. So if I reduce this picture down to the essentials, there is an attraction when vibrating objects move together, and repulsion when they move in opposition. This is just the dance you have to do with your hands, you know. These are repelling and these are attracting. There is an attraction when objects circulate in opposite directions, and a repulsion when they circulate in the same direction. Circulation and vibration define a spherical space within a minimum area given by Planck's constant, and a radius determined by the center's position and momentum. This is a way to describe the uncertainty principle. The number of such spheres in a given space determines the density and the amount of uncertainty present. Denser space will be heavier, more uncertain, and have a stronger gravitational field. It will also bend light more than less dense, less uncertain space. The more uncertain space is, the more power it has to change the course of things. This is why uncertainty is critical for an understanding of gravity, and why an understanding of gravity is necessary if you want to imagine an atom. Thank you for watching this video, and please tune in to my next one.